So as we said, an isosceles triangle is a triangle that has two congruent sides. That's it. For example, I see here, as you see in front on your screen, I showed you many triangles and many examples about isosceles triangles. If you see the first triangle, it has two congruent sides. How do we know this? If you look at the sides AB and AC, we use the same dash for both sides. When we put the same sign, any kind of signs, on two or more sides, we mean by that they are congruent or equal to each other. Another way to show that two sides are congruent is by writing the length of that side. For example, in the second triangle, to the right of the first one, we see that AB, the length of segment AB is 5 centimeters, and the length of side AC is also 5 centimeters. So AB and AC are congruent to each other, and hence triangle ABC is an isosceles triangle. There is also another way, a third way, to show that two sides in a triangle are congruent and it is isosceles. As you see in triangle ACB, the third triangle, instead of writing the measurement of the length of the side or put the same dash on both sides, we used another way. We wrote like below it, AB is equal to BC is equal to CA. So here the three sides are equal in length, not only two. So is it isosceles? Yeah, it is isosceles because it has two equal sides. But it has more. The three sides also are equal. This is another case in which we call the triangle not only isosceles but also equilateral triangle. But this is beyond our lesson. But you should know that even if the three sides are congruent, it's still isosceles triangle because it has the condition that two of them are congruent, two are equal. What about the last triangle down, as you see? Is it isosceles? Some might say it is isosceles, but I would like to ask you, did I put any sign on any of these sides, either the dash or the measurements or stating that they are equal? I didn't do this. So even if they look to you that they are equal and there is no given that says they are equal, we cannot assume it is an isosceles triangle. We cannot assume that the two sides are congruent. Hence, I would say this is not an isosceles triangle because simply I don't have enough information. So this is the definition, I repeat, of isosceles triangle. An isosceles triangle is a triangle with two congruent sides. Now, since we knew what is an isosceles or revised the definition, let's go to the isosceles triangle theorem. What does it say? The isosceles triangle theorem says that an isosceles triangle, or if, of course, what it means, if two sides of a triangle are congruent, like here, AC is congruent to AB, then the angles opposite to these sides are also congruent to each other. Now, when we say opposite, what do we mean? If you look at the figure here, I have side AC. Imagine you are standing on this side and looking to the front of you. Which angle is facing this side AC? It's clear, if you are standing here and looking towards this direction, you are going to see the angle B. Some students, they mix up and they might tell me it is BC. No, BC is not an angle, it is another side. So the angle facing AC is angle B. Similarly, if I'm standing at BC and looking in front of me, I'm going to see that what is facing me is angle A. So angle A faces angle B, faces side BC. And since AC is congruent to BC, then angle A is congruent to angle B. That's what the theorem says. If two sides are congruent in a triangle, then the angles facing them are also congruent. And in our lesson today, we are going to prove this theorem. First explain it and then prove it. By the way, the sides that are congruent, we call them legs. So AC is a leg and BC is a leg. While the third side, we call it the base. Even if it looks like it's not at the bottom of the triangle, it doesn't have to be at the bottom. The two congruent sides that have the sign of congruency are the legs. This is the base. Okay, so this is the isosceles triangle theorem. Before we give the proof, let's see some examples. If you see the upper triangle on the right, let's see, we have here three congruent sides. Still, as we said, it's isosceles. I will choose two of these sides, this side and this side. Which angle faces them? It's this angle 60 on the left and the other angle 60 on the right. And as you see from the example, they are congruent. They should be congruent because they are facing two congruent sides. I can choose other here two congruent sides. As I see, the three sides are congruent. Let's go to the second example. Here, which angles do you think are congruent? If you remember, and as we said from before, we cannot assume they are congruent because even if AB looks congruent to AC, there is no given information that tells me so. So here I don't know which are congruent to which one. We will go to the third, to the green triangle down. You see that this side on the left, the first leg it's V1, V2, its length is D. It's the same as the other side on the right. Also has the length D. So they are congruent. Now I look which angle faces it. The first side faces this angle here, and the other side faces this angle. And as the isosceles triangle theorem says, they should be congruent. And as you see, both angles are congruent and equal to 72 degrees. The third one is also another example. You see these two dashes on each side showing that side BA is congruent to BC. So what do we deduce from it? We deduce that angle A is congruent to angle C. By the way, later you are gonna learn the converse of the isosceles triangle theorem, which says if the base angles are congruent, then the sides facing them should be also congruent. But this is another theorem. Okay, let's move now. Now, how I'm going to prove the isosceles triangle theorem? In other words, the given says I have two congruent sides. How can I prove these two base angles are congruent? Usually, to prove something, we have to use previous theorems that we learned from before. So, for example, if I want to prove two angles are congruent, where did I learn about congruent angles? I learned, let's say, in parallel lines cut by a transversal. I learned like alternate interior angles, corresponding angles are congruent if they are formed by two parallel lines intersecting a transversal. But here, as I see, I don't see parallel lines anywhere, so I cannot use any of these. I learned also about congruent triangles. If I have two congruent triangles, then their corresponding angles will be also congruent. So let's see, can in this triangle ABC divide it into two triangles and try to prove that these two triangles are congruent? And of course, these two triangles should contain this angle C and angle B. I think so. Let's see. If I draw a segment from A to the base, and this segment bisects the vertex angle A, then we are gonna get two triangles, and hopefully we can prove these two triangles are congruent by one of the theorems that we know, like ASA or SAS or SSS theorem. Let's first divide it. So here is the triangle. As you see, I split it into two smaller triangles. I drew the, as I said again, the angle bisector of A, which I will call AD. And now, by definition of angle bisector, it splits the angle into two congruent parts. So angle BAD, this angle, is congruent to angle DAC, this angle. This is congruent to this angle. The two triangles, you can see them, right? This triangle ABD and this triangle ACD. So in these two triangles, what congruent elements do I have? As I said, I have first this angle is congruent to this angle because of the angle bisector AD. And also we have side AB is congruent to side AC. If you remember, this is the given. This is the given. It says if two sides are congruent, then we have to prove the base angles are congruent. So side AB is congruent to side AC given. This angle is congruent to this angle by definition of angle bisector. So I have up till now side and angle. So I need another thing, either another angle or another side. So let's look. Yeah, we have one side. That's it. AD. AD is common to both triangles. Both share the same side. So AD is congruent to itself. AD in the first triangle is congruent to AD in the second triangle. So these two triangles are congruent by side, angle, side. As you see, the angle should be included between the two congruent sides so that we can use SAS. Side, angle, side in the first triangle are congruent to side, angle, side in the second triangle. So the two triangles are congruent by SAS. How do we write now the proof? I know that you know the proof. We have to draw a table or split the page into two parts. Write on one part the statement and on the other side the reason. Some students think this is difficult. I know it's hard at the beginning. But writing the steps is something logical. So if you understand what you are doing, you see that each step is like a flow chart. Each step flows or is the result of the first step. Usually we start in the first step by the given. The given that we know that isosceles triangle theorem says, which is AB is congruent to AC. I wrote it, AB is equal to AC. What is the reason of this? It's the given. I've been told this. Then, as we said, because we plan to split the triangle into two parts, so we are going to draw AD. I didn't write here draw. You can say draw bisector AD that bisects angle BAC. I write directly AD bisects BAC. Each angle has one unique angle bisector, of course. This is the reason. What it means it bisects, it means angle BAD is congruent to angle CAD. So this is step 3. It comes from step 2. Since it is a bisector of this angle, it splits it into two equal parts. Angle BAD equals angle CAD. BAD equals CAD. This is the definition of angle bisector. Or you can say the angle bisector divides the angle into two congruent angles. The fourth one, AD, is congruent to itself. AD is congruent to AD. That's what we say a quantity is equal to itself. This is what we call the reflexive property here of congruent segments, because we are talking about congruent segments. So in this step 1, step 3, step 4, we prove the two triangles are congruent by S, included angle, and S, side, included angle, side. So we can conclude then in step 5 that ABD, triangle ABD, if you see in the figure, look at the figure, triangle ABD is congruent to triangle ACD. As you see, while I am naming them, I should name the corresponding parts to the corresponding parts of the other triangle. So if I say AB in the first triangle, I should say AC. If you look here, A corresponds to A, right? B corresponds to C. So if I write here B, in step 5, I should write on the other side C, because B corresponds to C, and D corresponds to D. It's common. Those two triangles are congruent, as we said, by side, angle, side. Finally, we reached the proof. We reached what we want to prove. We want to prove angle ABC is congruent to angle ACD. Since these two triangles are congruent, all their parts, what do we mean by all their parts? All their angles, which is 1, 2, 3, and all their sides will be congruent to the corresponding sides and angles of the other triangle. What I mean, this angle in particular will be congruent to this angle. This angle will be congruent to this angle here, if you see the figure. This side will be congruent to this side. But what I need here is only angle ABC, which is this one, and angle ACB. So we say angle ABC is congruent to angle ACD, and the reason when we prove two triangles are congruent is corresponding parts of congruent triangles are congruent, or shortly CP-CTC. So we proved the theorem, which I will repeat again. It says if two sides of a triangle are congruent, then the angles opposite to them are also congruent. And I forgot to tell you, of course, this is the first part is the given, so we write it as given, and this is the part that we should prove. We should prove that angle ABC is congruent to angle ACB. Let's see some examples about this theorem. How can we use it to solve some geometric exercises? You see here, I have these two triangles. From the signs that you see here, it says this side is congruent to this side, congruent also to this side. So I would look at the figure first, try to read many times the given. The given is here given in numbers. So here, as you see, I have this angle is 50, this angle here is 40. The other angles are not given, they just labeled, they gave their names. This angle 1, this angle 2, this angle 3, and angle 4. That's why they ask us find their measures. As you know, from that theorem I learned, if this side is congruent to this side, then the opposite angles should be congruent. So angle 1 should be congruent to angle 2. And I know that the sum of the angles in a triangle is 180 degrees. Since the third angle here is 50, then how much is left? How many degrees are left for the other two? All is 180. We subtract 50, and we get 180 minus 50 is, of course, you're going to calculate it, 130. So the sum of the measures of these two angles is 130. And since both of them are congruent, then each one will be half of 130. If we use a calculator or we divide it, it will be 65 each one. So this is 65 and this is 65. In similar way, we will look at this triangle. Here we have this side is congruent to this side. Then again, I'm standing here, so this angle should be congruent to the angle opposite to this side, which is angle 3. So this is 40. This also should be 40. Right, because they are congruent. 40, and since they are asked us to find angle 4, 40 plus 40 is 80. The three angles should be 180. These two are 80, so what is left for 4 is 100. So angle 4 measure is equal to 100 degrees. These are the answers here. This is the end of the presentation for today.